Hi. So we shall discuss about some random topics which was already covered in the first course of complex analysis. Let us begin with Cauchy's theorem on disk. So the statement is familiar to you. Let me not explain that. But one thing you have to keep in your mind is that here the integral is over a closed curve, over any closed curve gamma in the unit disk, in the disk delta. But this gamma, uh, if it is not mentioned otherwise, gamma is assumed to be continuously differentiable. Okay, so that's a crucial assumption. So whenever we talk about integral over gamma f z dz, we assume that gamma is continuously differentiable. It means it has a parameterization which is continuously differentiable. That is a very important thing. And another thing is that uh, the result which is valid in the disk delta, so the delta can be replaced by several other domains which you have already seen. Also, this gamma can be replaced by, in general, cycles homologous to 0 and several other things. Okay, so these are the generalized Cauchy's version, Cauchy's results which you have seen in the first course. Okay, now from this, let us deduce the Cauchy's integral formula. So first important thing is that you should keep in your mind that this result also holds true even with finitely many singularities, but they are all removable singularities. I mean, they should satisfy this property. Then also this result will hold. So hence we can apply this result for if small f is an analytic function on delta, and if you define capital F z in this way, then A is the only point of singularity which satisfies this property. So you can apply this Cauchy's theorem here, and after a bit computation, what you obtain is the Cauchy's integral formula. So this is the Cauchy's integral formula. So here is the result where in general eta gamma zeta is called the winding number. You know the definition of the winding number. This indicates the winding number. So this is the Cauchy's integral formula. So now look at the Cauchy's integral formula. So the left hand side, apart from this constant, I mean this winding number, this f takes values in delta, in the disk delta. But on the right hand side, we are integrating where we only need to know the value of f on the boundary. I mean, along the curve gamma only. Okay, so that is a very important point. So if you know the values of f on gamma, you are getting value of f at some points inside the usually typically interior of the disk. So that is one advantage of Cauchy's integral formula. So now let us see some applications of this Cauchy's integral formula. First thing is that for an analytic function, we assume only differentiability in a neighborhood of a point. Okay, but using this Cauchy's integral formula, we can actually show that the analytic function admits all derivatives of all order. Okay, so you look at the Cauchy's integral formula, and if you are able to differentiate under the integral sign, this here I used interchange of order of differentiation and integration, but that is admissible. I think you might have proved some technical result using that in the first course, which will let you differentiate, and f dash z you will get like this, f second derivative you will get like this, and keep on doing that. You get the nth derivative in this form. So this tells you that an analytic function admits all derivatives of all order. Okay, so now yeah, now look at here. So now we use this higher derivatives. Now yeah, you start from f and you look at the function f1z defined in this way. I mean at z equal to a, you define it to be f dash at a. So then here also you have a removable singularity only. Now what happens is that fz can be written in this way. In the deleted neighborhood of a, fz can be, so with this definition, fz can be written in this way. So f of a plus z minus a into f1z. Now look at f1z. At z equal to a, this limit goes to f dash a. Therefore, that was a removable singularity. So f1 is analytic in delta. And moreover, f1 of a is f dash a. Okay, so fz you can write in this way. Okay, in the deleted neighborhood of a. Now you repeat this for f1. and f1 can be written in this way, where f2 is an analytic function, and you keep on doing that and substitute it in the expression for fz. So finally you will end up with this. So let me skip that. Yeah, finally you will end up with this. Fz is equal to f of a plus f dash a by 1 factorial into z minus a plus f double dash a by 2 factorial into z minus a square plus etc. And the nth term is this, f n minus 1th derivative at a by n minus 1 factorial into z minus a power n minus 1 plus an analytic function f and z into z minus a power n. So this is the expression. This is a finite Taylor development. Okay, and here f and z will be analytic. That's it. Okay, so this is the finite Taylor's theorem or Taylor development of an f of a function, analytic function. This you can do at any number of times, because each time you repeat this, you will have the nth level. You will obtain the nth level Taylor development. Okay. Now we are bothered about the remainder term. So here we are writing fz. See, look at the first five terms. They look like a polynomial. So it is actually a polynomial, and only the nth part or n plus 1th part is some analytic function is involved, which need not be a polynomial. So it is just like a polynomial. Okay. So now you look at the remainder term. So the nth term is f and z into z minus a power n. So you look at the remainder term f and z. You apply Cauchy's integral formula. You will have this expression, which you can easily prove. And what happens is that using this expression, you will get this estimate. It's very easy. So the absolute value of f and z will be bounded by this quantity, and that is very important. Now you look at the expression once again. Fz is this, with f and z has this estimate, remainder estimate, which I just mentioned. Now you assume that f at a equals 0, f dash at a equals 0, and so on. I mean, nth derivative of f at a equals 0 for all n. So in that case, what happens is that all the f of a, this part is 0, first term, second term, everything will be 0, and only the nth term will remain. That means f of z will become f and z into z minus a power n. And you use the estimate which we obtained just above, and your absolute value of fz will be bounded by this quantity. Now this is applicable for every n, so you let n tend to infinity. What happens? This quantity will go to 0, because mod z minus a is bounded by is strictly less than r. In that disk, what happens? This goes to 0. Therefore, f of z will be 0 in that disk. So what happens if we assume that f is 0 and f at a is 0 and f dash at a is 0 and all the derivatives at a equals 0, then what happens that in a neighborhood of a, you will get fz is identically 0. Okay, so that's what we obtained. Now what happens is you can improve this result. Here we proved that f is 0 only in a neighborhood. In fact, if f is defined in some region, by a region I mean an open connected set, then if f satisfies this assertion, that means f and all its derivatives vanish at a, then we can actually prove that f is identically 0 in omega, the whole omega. So that proof is very easy. We just split this omega into two subsets. In the first set, all f and all its derivatives vanishes. The second set is that sum of the derivative or fz is non-zero. And you will write omega as E1 union E2, and you will prove that E1 and E2 are open sets. So that will contradict the connectedness of omega. In fact, we proved that E1 is open just now, because we assumed that f and all its derivative vanish at a, means in a neighborhood of a it vanishes. So E1 and E2 are open sets, and therefore by connectedness you will get that one of them should be empty. So we have already assumed that f at a and all its derivative at a is 0. So this E1 is non-empty. Therefore E1 is the whole set omega. That means f is identically 0 in omega. So this is a very important result. So it tells you that if you assume that f and all its derivatives vanish at a point a, then it will be identically 0 in omega. So that's what we proved. Okay. So now let us apply this result